Hey everybody, this is Courtney Brown and Emmy Jakob, and we will be discussing our Chapter 3 presentation, which is on the general methods for generating random variates. So the first method that we're going to discuss is inverting a CDF, or the inversion of a cumulative distribution function. So with the inverting of a CDF, we look at if x is a continuous random variable with the CDF capital F, and r is a uniform from 0 to 1, then the random variable f inverse, or f raised to the negative 1 of r, has a CDF that is f. That is basically the definition of it. So an example of using an inversion to generate variates from a distribution with a density f of x is equal to lambda e raised to the negative lambda x on support 0 to infinity, which is our exponential function, or exponential PDF, sorry. We basically look at f of x, so capital F of x is equal to the integral from 0 to x of the lambda function, du, and we find that that's 1 minus e to the negative lambda x. So basically we've taken our distribution function and evaluated it from 0 to x. Then we take r to be the 1 minus e to the negative lambda x, solve for x in that, and we end up getting negative 1 over lambda times the natural log of 1 minus r. And since r has the same distribution as 1 minus r, we can basically just use r instead of 1 minus r. And then to take a sample random variate x, we set the value of lambda. So if x is equal to negative 3 natural log of r, and lambda is equal to 1 over 3. So then if there's the next random number is r is 0.1367, then the exponential variate is 5.970. Again, once we plug that in, as you can see on the left, you've got x equal to negative 3 natural log of r, which gives us our 5.970. Unfortunately, there are some limits to inversion, and some of these limits is that many standard distributions do not have closed forms for f inverse. So basically what we're looking at then is, although x can be solved numerically, it's much slower and should be avoided. So we can look at, for table 3.1, that there are some common standard continuous distributions that have closed forms of inverse CDFs, or f inverse. And we can see this below. So the first one we can look at is the Weibull distribution, which is given as f of x here. You got alpha times lambda raised to the alpha times x raised to the alpha minus 1 times e to the negative lambda x raised to the alpha. And then we're given our parameters and given our supports. The second one we can look at is the logistic distribution. Again, these are continuous distributions, given as follows, with the parameters that lambda has to be a positive number, on supports negative infinity to infinity. And the last one we have is the Cauchy distribution, which is 1 over pi times 1 plus x squared. Now this one doesn't have any parameters to keep, so in other words, x can be any variable. Positive or negative has no constraints on it, and supports are negative infinity to infinity. So the second way we can do it is we can do an envelope rejection. So basically when there's no closed form for the inverse of f and we want to sample variates from the density of f that is a proportion to some non-negative function h, we can do two things. We can choose another distribution, say g, and g has supports if h is a subset of the support of g and g of x is greater than or equal to h of x. And we can accept y with the probability of h of y over g of y, or reject variates that do not have the same desired distribution. And we repeat this process until we get a prospective variate is accepted. Now, the idea with this is we want to alter the relative frequency distribution of y values to the probabilistic rejection step. And the accepted ones most precisely have to have the required distribution f. And then we can graph the function g. And on the graph, the function g majorizes h. So what we'll see is then on every single x, the function g is larger than every one of h, with a correct lambda. Alright, so the last way to do random variates is to use a ratio of uniform methods. This is basically when you take two independent uniformly distributed random variables, and we'll set them as u, which is from 0 to 1, and v, which is from negative a to a. And we're saying that a is a known positive constant. What we can do then is we can create a new random variable, x, by taking a ratio of the two independent uniformly distributed random variables we created above. So as you can see there, the random variable x is created using v over u. So then we can also do some joint densities, right? We've got a density for u and a density for v, and now we've created a new random variable x, so we can have a density for those as well. And by doing a joint density, we can look at the first example, which is if we set u and v for a joint density, we can say that over the supports, if we set u from 0 to 1 and set v from -a to a, again where a is a known positive constant, we look at a joint density of 1 over 2a over those supports. Likewise, if we look at the joint density for u and x, again x being v over u, then we see that the joint density is u over 2a. And with over the supports, xu is between -a and a, and u is between 0 and 1. Now we can also look at the marginal density of x. So for the marginal density of x, again, this is where we start getting close to a. We say that for the absolute value of x less than a, so basically inside the rectangular form that we're creating, because we're creating a rectangle that's basically got the vertices of 0, 1, and -a to a, we say that inside that rectangle, the marginal density is 1 over 4a. And if we look at outside of that rectangle, in other words, where the absolute value of x is greater than or equal to a, then we look at the marginal density to be a over 4x squared. So let's continue. Now, Kinderman and Monahan in 1977 basically said that they theorized that instead of using a ratio of formulas over the rectangles 0, 1, and -a to a, which is what we had done before, the theorem says that basically we can now look at this distributed over a subset of that rectangle, 0 to 1, -a to a. Now we have two theorems that we look at here. So in theorem number 3.1, which is what's designated in our book, basically we have to allow for three things. We have to let h be any non-negative function with its integral over its supports, which has to be less than infinity. So then we let c equal a function of u and v, where u is between 0 and the square root of h, the function h, using v over u, and then v over u is within the support of h. And lastly, we want to let the point uv be uniformly distributed over c, and let x again equal v over u like we've done before. When we do that, then the probability density function of x is the function h of x over the integral of h of x from -infinity to infinity. Now for theorem 3.2, we have to let a few things happen, obviously. Because when we let c equal the same thing we had in theorem 3.1, but we let u plus equal the max of the square root of h of x for all x. Let v plus equal the max of x times the square root of h of x for all positive x. And let v minus equals the minimum of x times the square root of h of x for all x less than or equal to 0. And then we let d equal basically a rectangle from 0 to u positive, u plus, by v minus and v plus. We have that rectangle d. So what that means is then c is a subset of d. And again, these are two theorems that basically are provided by Kinderman and Monahan, which basically prove, or at least theorize, that a rectangle can be uniformly distributed over a subset of that initial rectangle. So thanks for watching, everybody.